So the next speaker, and actually is the last speaker regarding the vendors, is Mario Armelao from SCIEX. Thank you. Mario, actually I have here his bio. Mario has a background in biochemistry and has worked in the industry for about 15 years and is currently the specialist for high resolution accurate mass systems for the south of Europe at SCIEX. And I think he will tell us amazing things about the new Zeno and other things. And also, while you guys are setting up, I use this opportunity to thank once again all the vendors that have been very generous to sponsor this event. Stage is yours.
Yeah, right now. Okay. Thank you all. Thank you very much. Thank you for the very nice introduction. And thanks to the organizer on behalf of SCIEX to give us the opportunity to make this presentation. In fact, I think so far it has been quite interesting. Some topics have come up which are clearly important for single-cell proteomics. In my presentation, I'm not going to focus on the basic concepts, but I will surely try to highlight some of these concerns that have been raised. So the presentation, of course, will focus on two strategies towards low-level proteomic samples using our novel Zeno trap. So keep in mind that historically, the single-cell field started with essentially one vendor, then it went for the second vendor as well, and now there's a third one, which is SCIEX. So we're the new kid here, and part of the concept of today's presentation is to show you what's all about the new tech, how it is different, and how it will impact the performance of low-level proteomic samples. So just to give you an overview, I'll start by showcasing the hardware, pointing to the key critical differences that will impact performance, and then focus on the two strategies. Of course, the previous speakers already had the work and were very nice to introduce these two approaches. Essentially, what the next speaker will talk about, or not exactly, but as is very well known about that, which is SCOPE-MS. And the last point will be data-independent acquisition for extreme low-level samples. So the first thing is to show you the system. This is the Zeno. It's actually a very compact benchtop QTOF. It's essentially the size of a triple quadrupole, and it has three key differential features when we launched it, which was essentially 1 year ago. I'll start with the last one, which is the software. So now we use the same software, whether you have a triple quadrupole or a QTOF-based system, which makes it much easier both for data acquisition and processing. Well, in proteomics, you'll need other tools for sure. But in terms of hardware, the two key differences is, of course, the first one is that we introduced novel fragmentation techniques. Well, that won't be necessarily the feature that I will focus the most today. What I will focus really is one of those features, which is the one that promotes what we claim is really the best MSMS sensitivity as a high resolution system. So looking inside, you can see the flow path of the ion path of a QTOF based system. You can see that the time of flight is essentially doubled. So that's an N shape. That's why it's so compact. And you can see, I would probably highlight as well on the box on your top left corner that you can see that the ion source that's featured here is already the OptiFlow version for the 7600, which actually makes a significant difference, not only in nano, but even more so in microflow. Regarding the key hardware change, I should highlight the two novel ion traps. The first one is the D cell, the one I'm not going to discuss more about today, but you should check it out, especially if you're interested in PTM analysis. And if that's your point, you realize that sensitivity was an issue. So that's why it goes hand in hand with the clear focus of today's talk, which is the Zeno trap. The Zeno trap is that orange section that appears after the collision cell. So that's a linear ion trap. So that's your first hint. That's a very high capacity ion trap because it's actually a section of a quadrupole. And the second hint is that it comes after Q2. So you already guessed that will only operate at MSMS level. So that's very important when you think about the other two ion traps that you've seen today, either upfront or as the main analyzer. So the key point about the Zeno TOF is to solve an issue that all QTOF-based systems have, and that's a limitation in terms of duty cycle as the ions come out of the collision cell, namely the fragments, and are pushed towards the time of flight. So in effect, what is publicly published as a limitation of the technology is that QTOF-based systems will have typically between 5 and 25% duty cycle maximum. And this range is related to the way the ions exit that collision cell. So if you see the animation, as the fragments exit, the smaller M/Z fragments move faster than the heavier M/Z fragments. And therefore, there's a dispersion here that makes that only a fraction of the ions are actually in the optimal spot to be pushed to the time of flight, and the remaining ions will be lost. So this is why the duty cycle at this part is limited for QTOF-based systems. And if you have the curiosity, you can check for every vendor. Their published duty cycle will be within this range. So notice as well that the 5 to 25% means that typically the faster ions are the ones that are less transmitted, while the bigger ones tend to be more efficiently transmitted. Now, what SCIEX did is that we used actually the IQ3 lens that already existed and applied a new one, which is the Zeno gate. And what this creates is a small section that is a quadrupole linear ion trap. And this allows us to trap the ions. And keep in mind, although we don't want to do mass analysis, this is not the key point of this ion trap. What it exists for is to in a very fast way, to order the way the ions exit this trap, namely in reverse order, so that the heavier ions are released first and the lighter ions are released last. So this allows us to synchronize the moment the ion packet arrives for the TOF to push it. So by this technique, we essentially restore the duty cycle of a QTOF-based system to over 90%. So essentially, we restore the duty cycle for the entire mass range. And immediately you guess, okay, we have now very high MSMS sensitivity, and that's why we're addressing the topic today. So the first stop is, of course, the first strategy, which would be a label-based strategy. And the labeling-based strategy, I think, was mostly highlighted today, probably not enough on the carrier channel and the impacts of that, but I would recommend that you either read the papers or watch the channel of the next speaker, which will have some presentations that cover those limitations. So the reason why some customers immediately approach SCIEX for this application had to do with two factors. So the first one is, if you look at the increase of the overall signal in the spectra, when you compare the spectra with Zeno TOF off versus Zeno TOF on, keep in mind this is data from the same system, you realize that the entire spectrum is enhanced. So regarding the peptide fragments, you'll see an average of 6 times increase in signal. But if you recall what I said before, the improvement is not linear, it's actually exponential as the M/Z decreases. So when you're working with isobaric tags, in this case with iTrack, the reporter ions actually have very low mass. And if you look at the theory, the mass of these fragments are actually increased over 10 times when Zeno is activated. So you can see on the frequency distribution on the right, that when Zeno is activated, the reporter ion area moves one order more to the right. So this is highly beneficial for this strategy in the sense that it improves quantitation by improving the signal of the reporter ions. But the other point to consider is the size of the ion trap, right? Because when you relate that to the type of effects that, or negative effects that you can have with a carrier channel, I mean, for those of you who are maybe more aware, you realize that the size of the trap matters, even in other instruments as well. So that's why they're used, preferentially the ones that had the biggest ion capacity in order to mitigate this issue. So the capacity of the Zeno trap is the largest. So just so you have an idea, it's roughly 7 times the capacity of a C trap, which is not the analyzer, just the transfer trap. And just to give you a rough estimate, actually the data here is extracted from the from EOR's poster at the SMS, which you can find more data on this topic. But Zeno not only improves the number of identified protein groups, but more importantly, benefits quantitation, which is the whole point of why we're doing this. So the data here is published. You can read it if you were interested in finding out more. Now, the novelty about this system was only released this summer, and that's when we activate xenopulsing also for data-independent acquisition. And to be frank, whenever we're talking about data-independent acquisition, we're talking about a very specific type, which is SWAT. So independent, if you have mobility before or after, you're always doing some sort of SWAT, MS. And when we went to test this, and you can see here the sample data, we started with what is now the default, 200 nanograms. And you can see that activating Zeno for the SWAT acquisition immediately improved the TIC for the MSMS signal dramatically. But even more so, when we started to dilute the sample, we realized that the lower the sample amount, the better the statistical impact of having Zeno pulsing activated. The consequence is as you would expect. So you can see at the level of the spectra, you can see it in mirrored mode, the overall intensity increases, but always keep in mind, if you go and measure the signal to noise on each individual fragment, you should expect that signal to noise to improve as the M/Z decreases. In terms of quantitation, when you extract, you can see the benefit as well with a significant increase in intensity. And I would also remind you that the benefit of having all this sensitivity is the ability to, one, go faster, and two, be more specific. So use more variable windows. So for your information, the MSMS accumulation time in this example was 12 milliseconds. And starting with this, we wanted to go down in dilution, see where we could reach with this new capability. So we started at the 200 nanograms, and we at least were already very happy to see that the numbers were quite impressive for us, at least, because we're the ones entering here, and you'll be the judge of that. But what I think is really relevant is and this is something that SCIEX shows, is the number of protein groups that you can actually quantify with high reproducibility. Not only that, but you can even see the number that can be quantified with CVs below 10%. So that's very much SCIEX. The other point to signal at the 200 nanogram level is the benefit of running what others call direct DIA or library-free SWAT. The benefit of using the software tools such as Diane allows us to run this data acquisition without having to go and do the library first. And having this level, we started the dilution. So you can see already at the 50 nanogram level that the performance is still very interesting, especially regarding quantitation, and we further decrease down to the 5 nanograms. And at this level, we show the difference, of course, versus when we didn't have Zeno SWAT activated for this feature, you can see that not only the identification number is benefited, but especially the quantification is really improved by having Zeno. And the other point that I would like to highlight is that we try to always blank, so that we like to see those identification rates at 0 with the blank. Otherwise, as we go down, carryover may be an issue. Perhaps another point is to highlight that both gradients and columns make a big impact at this level. Just switching the column can have a profound or a significant difference when comparing results. So keep that in mind. So for example, at this IMaSS, Synoptics showed their prototype for the OptiFlow, which had very nice numbers starting from 250 picograms. And I would also say that the columns that my thermo colleague mentioned work really well, especially doing DDA long gradients. If that's what you want, they work well. That's on the poster by ER, if you want to check that out. And with this, we wanted to go further down, further to the 250 picogram level. So we continue to dilute and always keeping the blank there. And you can see the levels that we reach at 250 nanograms, of course, with the 45-minute gradient, which you would compare to the 30 SPD method. And we showcase that we can ID these proteins, so above 1,000 protein groups at this level, and we can, most importantly, we report the number of protein groups that we can accurately quantify. So, of course, you don't have to be so extreme. Maybe you want to work in a more comfortable range, such as 1 nanogram or 5, and you can see that at that level, it's not only much easier to work, but the numbers are even much more interesting. The other thing that we do in this case is to try to compare a little bit the different approaches between DIA with library, DIA library free, and then using DDA. I would say the poster has more updated data, but we see a nice overlap. Of course, DDA suffers the necessity of having longer gradients, but the benefit of the multiplexing is, of course, there. So it's your approach. One important feature to demonstrate is this robust, is it reproducible? And in order to try that, we use the same system over a period of several days, and you can see here the dates at which this was run, and without cleaning the system and running other proteomic samples on the system, we came back and did the same samples, as you can see here, to see how it would behave, and you can see that it behaves as is expected, not only at the detection level, but also at those that are very reproducible for quantitation. Early on, I mentioned that IMaSS was the main issue about the system, the quality of the IMaSS, because that's the whole point of solving the duty cycle. So the point is, can we extract data at this level? Is it real? Do we have the data? Can we see it? Can we compare it? So we proceeded to select series of peptides, protein, and extract that data, where you can see the peak profiles, and they're all coeluting. You can see the spectral data. And of course, the consequence of this is that we have a very nice, you can see a complete Y series. So, okay, for sure we can detect. But remember, not detect, the point is, can we? So you can see here we have the individual peptides as well as the total summed peak area. And you can see the response from the blank all the way up to 25 nanograms. So you can see that it responds as expected. So when it comes to quantitation, you can see that what's important really is to extract these peptides and to be able to quantify them, right? And as we sum, we go to the, and we can see that the CVs that are achieved are in my opinion, then really impressive. This is very accurate quantitation at an extreme low level. And we can do this for this peptide, perhaps with cherry picking. So we went to a 10 times lower abundant peptide to confirm our hypothesis. And as you can see, of course, if we decrease the intensity, the spectrum starts to show a little bit more noise, and still a quite decent series. And the response is still as expected. More importantly, the percent CV is very good. It's below 10%. That's what you should want for quantitation. Just a final comment, and with this I conclude, is to say that there are different ways to report reproducibility. One of them is to report averages. Remember, averages are not the same, and I'm not going to guarantee that your protein is actually reproducible. So with this, I would just like to give you the concluding highlights. So Zeno SWAT really drives sensitivity, right? So we improve the sensitivity dramatically, especially at the low abundant samples. The improvement is even more markedly. We can now go free, and everyone is showcasing that DIA outperforms DDA for identification, quantification, at least without considering multiplexing. And that the same system, so keep in mind, this is not modified Xenotoph, it's the same Xenotoph can go this low or work with higher abundant samples. So it's the same system. And the same system, due to the quality of its MSMS, is showcasing this level of reproducibility down to samples this low. And with that, I would like just to thank IR, which really produced this data in the US, as well as Jose Castro, which is the product manager and in charge of the Zeno development. And last but not least, just to plug this one, we have a technological seminar with DASP here in Milan. So please check it out if you want to attend. I think there are speakers here that will also be present in that event, and will cover multiple application areas. So thank you so much. Thank you for your time. If you have any questions.
Thank you very much, Mario. So while I scan the QR code, questions?
Always ask the stupid questions, yes. It means it was unclear which HPLC you're working in the presentation. You did not really mention this.
Yeah, I didn't mention SCIEX is agnostic, LC agnostic. But in this case, we used the Waters M class.
Okay.
So we can either use the Waters M class, we can use the EvoSep. I think both work really well. I think the key feature is the column. And the lower you go, the more impact the overhead times can take. But if you go fast, that's less important.
But you're not fast. Your runtime is 1 hour.
No, for this application, I'm just now opening the field. So you should consider all possibilities. Now, in this case, we're running at 45-minute.
That was the gradient time.
Yes.
Not the runtime.
Yes, when you consider the M class.
But
if you consider the EvoSep 1 is a different cycle time.
Yeah. You still work with high flow rates, yes? Or with 150 micrometer columns, yeah? That means you did not really work with a nanospray column. The system is equipped with a, how can I say, a normal spray column.
You saw that the column was 150. So you typically compare with 75 or even narrower columns. I did highlight that we had data on the thermo column on the poster, which you can find on SCIEX site at the SMS posters from this year. But typically, we see that the system, or let's say the method, is more robust. Let's say the least narrow the column is.
Yes, then you should work with a 4.6 millimeter column. That's the most robust column, yeah? A second question. A long time ago, a scientist, it's called Markus Ralser, probably you know him, yes? he published a paper about scanning SWOF.
Yes.
On the instrument that
7600
or something. Yeah?
No.
7500. Yeah. Yeah.
He published this on the triple TOF.
On the triple TOF.
So
yeah. It was the triple TOF 6500.
6600.
66.
So
yeah,
this is the 76, and the other one is the 66. So the triple TOF product line is the 66, which Marcus published. He published as well in the UK first with the 56, always focusing on high throughput, on starting with the micro approach for that characteristic and ending up with analytical columns at 800 microliters per minute, right? With scanning SWOT, which is what.
But I think the community is missing scanning SWOT. They would like to work with it.
No, scanning SWOT is an R&D product, is not a commercially available
since
product.
4 years.
Well, I can tell you that the original paper on Zeno pulsing was from 2009. Only when it's available can you work with it. So Zeno increases the overall signal tremendously on the IMaSS. So that creates needs for development on the hardware side. So you can see that now we are exceeding the scanning SWOT data on the triple TOF with higher robustness on the Zeno. And if you read the conclusions on the Marcus Galser paper on the Zeno TOF, one of the things that he highlights is that scanning SWOT is compatible with Zeno pulsing. So he opens up the door to its implementation along with Zeno.
When is it coming?
That you have to ask Toronto. So we never know those things. I mean, if it's R&D, we don't know when that's available.
Okay.
So we have time for 1 or 2 more questions. I do have a question. So my previous boss is a Zeno TOF and is bragging about how good your ETD is. And I'm wondering if you ever tried DIA ETD with your instruments.
Yes, we can do as well DIA ETD, but always remember it's always linked. So that's very novel, and it's always linked with software. So for example, a while back, I gave a talk on lipidomics. So now a paper is coming out with MS style processing EAD for lipidomics. But I mean, we do the hardware and you do the science. And nowadays, software development is really done by the community more and more, and it's open source. So that's a very important also step in the development of a system. So this is a new box, comes to the market. Another thing that your previous boss openly commented is why he was first interested on the Zeno TOF, which was for the intrascan dynamic range, which goes back to that scope MS approach.
How do you know my previous boss?
Because if it's the one bragging about EAD, maybe the one bragging as well about the dynamic range. Maybe does it publicly.
Okay. Any more questions? Perfect. Yeah, thank you very much, Mario.